All right. Today, what I'm going to do is review this assignment um, that was assigned for the weekend, which was the Dynamics AP Classroom assignment. Dynamics usually is used to describe problems that involve Newton's laws of motion. They often include some kinematics concepts as well, calculations. So I'm going to go over those problems in this recording um, so that students have an opportunity to kind of review their own thinking and their own answers. Um, and have the steps and the solutions available. All right. Let me just make sure I'm in the right mode here. Whiteboard mode, annotation mode. It should be. Coming through, yeah. All right. So for number one, now again, I apologize that your problems might have been in a different order. So I think I still had the scramble function or whatever feature checked off from the last exam that you guys did in AP Classroom. So in the future, I'll be more mindful of unchecking that so that everybody sees the problems in the same order. So it's just easier and avoids that confusion. So apologies there, but this was the number one. This was the first one that I had selected as I went through their bank of questions, create this assignment. Let me actually just grab my this. I feel like I'd like to zoom in a little bit more if I can. Not really sure what's going on with my mouse is not functioning beautifully. There we go. It's a little, maybe a little more. Yeah. All right. I guess it's the most I can do. All right. So this question involves an inclined plane. I noticed that it says it's a frictionless inclined plane. 2 kilogram block starting from rest slides 20 meters down a frictionless inclined plane from point X to point Y, dropping a 10-meter vertical distance. The speed of the block at point Y is most nearly. So I first noticed that the angle isn't given here. Which we may need to think about. And I'll also point out that the distances are given. Like this distance is 20, this distance is 10. So remember that since they said frictionless incline, we know that the acceleration down a ramp that's frictionless due to gravity is g sine theta. Store that to memory, as I've said. It shouldn't be something you want to necessarily have to try to work out, because a lot of these problems you do will reference. I'm sorry, give me one more second. So sorry, I appreciate you coming so quickly. Do you mind coming back in about 1 hour? That's okay. Thank you so much. Okay. Sorry about that. Somebody was wanting my attention. So g sine theta is the acceleration down a ramp in the x direction, right? It's the acceleration along that x-axis that we've created. Just know that sine, remember, sine theta is, I mean, you don't necessarily need the angle, pointing that out. Sine theta is opposite over hypotenuse, which means our formula can, instead of being g sine theta, can just be g times the opposite over hypotenuse, right? Because that is sine theta. Sine theta is the ratio of opposite over hypotenuse. So if this is the angle of the ramp, the ratio of opposite to hypotenuse is a 10 to 20 ratio. That's a half, right? So we know that acceleration would be 5 meters per second squared, which tells us that's a 30-degree angle because sine of 30 is half for that reason, because the ratio of opposite to hypotenuse is a half. So once you have the acceleration, you can then move forward with answering their question. Their question asked for the speed at the bottom of the ramp. My thinking would be to use the kinematics formula, v final squared equals v initial squared plus 2a L, if you want to call it for that, for delta x, where L is just the distance along the ramp. I know it starts with no speed at the top. So really, the final velocity would be 2 times the acceleration, which we knew was 5, times the ramp length, which was 20. And then I'd end up having to square root that because of the v final squared. So when we do 2 times 5, which is 10, 10 times 20 is 200. Our answer will be the square root of 200. Which when you do that out on a calculator, I believe is somewhere around 14. Square root of 200. Yeah. So it's approximately 14. 14.14 is what I got on my calculator for the final speed at the bottom of the ramp, which puts our answer at C. Notice that is most nearly. The speed of the block at point Y is most nearly. So these are approximations. That's fine. All right, so let's move on. Number 2. Second here. All right, the next one is here. All right, this says, what is the magnitude, same problem, just different question. What is the magnitude of the net force? Remember that, always forget to click that. So remember that the normal force and the y component of gravity, which is mg cos theta, those cancel. But these are a canceling effect. And we know there is an x component force right here, FGX, which is mg sine theta, which I encourage you to just memorize. All right, so if there is no friction, which they said, then the net force, they asked for the magnitude of the net force. That's unbalanced, right? Out of these 3 pieces, this is the unbalanced amount. If you didn't remember that, but you did remember A is g sine theta, you can remember that in general, when you take a mass or acceleration and multiply it by a mass, that turns it into a force. Any acceleration expression times mass is force. So I can technically multiply this side by m and this side by m, reminding me that, okay, mg sine theta is the one that I maybe forgot. But once you know that, they've given us the mass of 2 kilograms. G we're using is 10. This ended up being a 30-degree angle. If you didn't know that, you would have had to do inverse sine of opposite over hypotenuse, right? To get the angle. So that would be inverse sine of opposite, which was 10, divided by hypotenuse, which was 20. An inverse sine there. And when you do that on a calculator, make sure you're in degree mode. It would give you 30 degrees. So if you wanted to use the angle, again, you could put sine 30 there. 20 sine 30. I know that that's 20 times the ratio, again, of opposite over hypotenuse, which is 10. So the amount of unbalanced net force, which is right there, FGX, is E, 10 newtons. Moving on to the next one. Make sure I am recording, right? It's always my fear that I get to spend all this time doing something like this, and then I come back, I'm like, oh my God, I didn't hit record. I did. Let me double check. All right. Next question would be this one here. So the free response question I'll go over now. It says something is sliding down, a sled is sliding that has a mass of 25 kilograms. So that's the first thing I can write down, is sliding down a hill with a constant speed of 2.4 meters per second. So they describe it as a muddy hill, and for that reason, there's some friction. So there's a resistance to the motion down the hill, some force in the opposite direction. For that reason, it's just the right amount of force so that it goes down the hill without accelerating. It just slides down at a constant speed. The slope of the hill is given as 15 degrees. And that's it. First question, calculate the time it takes the sled to go 21 meters down the slope. Well, if they said it goes at a constant speed, then this is just constant speed motion, right? Distance equals speed times time, or distance equals velocity times time. So if we know that the distance down the hill was what, 21 meters, we're solving for delta t. Just doing some algebra here to divide both sides by the x, of course. You get delta x over vx. Delta x was the slope length, which was 25 meters. Sorry, it's a 25. 25? Oh, no, sorry. 21 meters divided by the horizontal speed that they gave us, vx. Remember, again, x-axis goes in that direction. 21 divided by 2.4. I get 8.75. Actually, exactly equal to 8.75 meters per second. So that would have been the answer to the first question. Oop, I'm sorry. I don't know why I'm saying meters per second. This is time. My apologies. The amount of time is 8.75 seconds. So the answer to part A is 8.75 seconds for it to go down the slope. On part B, on the dot below that represents the sled, draw and label a free body diagram. No components are supposed to be shown on this. We know gravity is down, Fg. We know that the normal force is always perpendicular to the surface, 90 degrees to the actual surface line. And then we know that there's some friction. Maybe I shouldn't have drawn that line there. Sorry. Shouldn't have done that. So gravity would have been down. The normal force would have been up. And then the friction force would be that way. Because remember, the motion is down this ramp. So the friction force would have to be opposite to that. You never include the velocity vector like I do on the diagram. Sometimes it's helpful just to put it off to the side so that someone can understand why the friction force is up at that direction, that angle, because the velocity is opposite to that direction. All right, C, calculate the frictional force. Calculate the frictional force. So we know that if this thing is going down this hill at a constant speed, because that's what they told us, in that direction, that means that there's no acceleration. That means that the horizontal acceleration, the acceleration of force, or the acceleration along this axis, there is none. There's no horizontal. There's no acceleration. I should call it horizontal, but because remember that our x-axis goes along that direction, x. So when we write Newton's law, which is F net equals ma, it depends on what axis we're referring to. So if we're referring to x-axis motion, then we're referring to x-axis acceleration. Those would have to reference forces along parallel or anti-parallel to that axis, or to that line. So along the line, or forces that are along that line, or in the opposite direction. You have to consider those forces, right? And add them up. That's the net force in that direction. So we already know, though, that the amount of force that's pulling it down the ramp is mg sine theta. That's the component of gravity that pulls it down the ramp. If we know that the friction force is in the other direction, and that it has to, these have to be equal to, right? This is 0. So m times 0 is 0. So that tells us that, again, the net, the sum of any forces along that axis, which would be the mg sine theta amount of force, and then the friction force, which is back this way, must be equal. Right? Those two forces must be equal but in opposite direction to cancel, so that there's no net force, no unbalance of forces in the system, and therefore it'll just maintain a constant speed as it goes down the slope. Right? So we already know then that the friction force, based on what I just said right here, have to be opposite but equal in amount, so that they add up to 0, like 5 and minus 5. Like if this was -5 newtons, then this would be +5 newtons. And we know that those would add up to, as it says here, 0. All right, so we know the friction force is equal to mg sine theta because of this description of the motion being constant. This is sliding friction, by the way, kinetic friction. And so we also know that there's an equation for the kinetic friction force. I'm going to erase that now. So if we know again that the sliding friction in general is Hmwk times the normal force, and we know that the normal force is mg cos theta, because the gravity component of in the x direction is mg sine theta. So that's the general expression right there for the amount of force. Again, if this was gravity pulling it straight down, this was the ramp like this, then this amount of force that I'm pointing to right here would be mg cos theta, which again means that the normal force will be exactly equal to that amount. The normal force will be mg cos theta, which is why we plug that in here, and it goes there. Right? And that's the understanding of it. If you want to just memorize it, go for it. I would recommend it. I mean, best scenario, you understand it and you memorized it. That memorized it being this. Memorize that. Umg cos theta is the sliding friction force on a ramp. But we just stated a moment ago that that amount of friction force in this direction, the sliding friction force, since it's moving again down the ramp at a constant speed, must be equal to mg sine theta, which is the FGX component of gravity pulling it down. Right? Those must be equal. So that means I should be able to set this whole thing equal to this whole thing. Right? Because I have an expression for this, and I have an expression for FGX. Yeah? Right? So I should be able to say, essentially I'm just making the statement that FGX must be equal in magnitude to the kinetic friction, sliding friction force. And now this one will be mg sine theta, which I'm about to write here, has to be equal to, now the big expression for FFK, right there, Hmwk mg cos theta. Sorry, I ran out of space there. So the question was, again, to calculate the coefficient of friction. We're on part D. Oh no, sorry, we're on part C, and then we'll go into part D with the same work. So for part C, calculate the frictional force. It's just mg sine theta. The amount of friction force is equal to mg sine theta. That would be your answer to part C. Calculate the friction force. So for part C, it would be mg sine theta. If they gave us numbers, which it looks like they did, 25 times 10 times, we knew this was a 30-degree angle, which was a half, then this would come out as 125 newtons. So the amount of force friction force is 125 newtons, which is the same as the amount of gravity force pulling it down the hill. For part D, they're saying, now calculate the coefficient of friction, which I was about to do over here. Right in here. So I know M and M would cancel, right? And it looks like G and G would cancel. This is nice. So that means I can just solve this algebraically for Hmwk by dividing both sides by cos theta. So the cos theta part would cancel, cos theta part would cancel. So I get sine theta over cos theta. Wait, that's an identity, geometric identity of tan theta. So that means the kinetic friction coefficient is equal to that angle, tan of that angle. That's actually the more practical way to determine the coefficient of friction experimentally for two surfaces. You find a very particular angle where it coasts down this incline. If you're interested in the frictional coefficient between whatever the incline is made of and the other material that the object is made of, you put the object on the ramp and you make the angle just right so that it slowly coasts at a constant speed down the ramp. If that's the case, then you can calculate the coefficient of kinetic friction like I just did on the bottom right by just measuring that angle. You can take a protractor out or do whatever you need to do to measure that angle, and tan of that angle will give you the coefficient of kinetic friction for sliding friction. So here I'm doing it, would be tangent of 30 degrees. Is this? I'm sorry. Oh shoot! Did I use the wrong angle before? I thought this was a shoot. Sorry. I guess it just changes this one answer for me here. I was thinking of the last problem, I guess. I thought this was 30 degrees or something. This is a 15-degree angle here. Sketching that, so sorry. Which means 250 times sine of 15. 250 times sine of 15. I get 64.7. Sorry about that. 64.7 newtons. These numbers would have been 64.7. Okay, so that's the only spot I actually made a calculation with the angle. So that's it. So coming up here, it would be inverse tan of, I'm sorry, not inverse. The coefficient of sliding friction would just be tan of 15. So I'm just using the equation on the bottom right. Maybe worth memorizing, I don't know. Some students can memorize everything, and yeah, throw that one in your brain if you want to. The coefficient, sliding coefficient friction is equal to tan theta if you're doing this experiment problem where it's on a ramp. It's moving down at a constant speed. So when I type in tan of 15, making sure that I'm on degree mode, I get approximately 0.27 as my coefficient. If it came out as 17, you'd immediately know that something's wrong because 99% of the coefficients are between 0 and 1. Maybe it comes out a little bit more than 1 if it's really frictional, like 1.2, 1.5, 2.1. But if you get some crazy number that's up in the 5s and 10s and 15s and 20s, it's probably a mistake. Coefficients don't go that high. All right, part E. The sled reaches the bottom of the slope and continues on the horizontal ground. Assume the same coefficient of friction. In terms of velocity and acceleration, describe the motion of the sled as it travels on the horizontal ground. Erase all this. Now, do I need any numbers as I move forward? The graph is next. I don't think there's anything else I need. I'm going to erase all of it. So then they're saying, describe the motion once it hits the bottom, assuming that the coefficient over here is whatever I think it was 0.27. It doesn't matter what the number is, but just knowing that there's friction here, and this thing comes down this ramp, what would the motion be like once it hits this flat frictional surface? That's what they've asked. Sled reaches the bottom of the slope, continues on the horizontal line, continues on the horizontal ground. Assume the same coefficient of friction. In terms of velocity and acceleration, describe the motion. Well, we know that it would move if we took snapshot images of it every second. Every second, it would move a smaller and smaller distance. These are all 1 second intervals of time until it finally stopped. So we know the acceleration would be negative. Acceleration is negative since the velocity is to the right. Decelerating. One description. Due to friction. And therefore the velocity would decrease. And it would decrease linearly. Friction always produces a slowing of speed with a sliding friction that reduces the speed in equal amounts each second until it stops, which we would say a linear decrease in speed, since the friction force is constant. All right. And then on a graph below, sketch the graph of speed versus time for the sled. Glue both the sleds travel down the slope and the horizontal part. Clearly indicate with symbols, like I've always asked you to do in arrows. TL, it says, I know the time at which the sled leaves the slope. All right, I think I'll get the question. Erase this. All right, so we know that when it's going down a hill, it's speeding up, gaining speed linearly, right? Accelerating as you go down a hill or a ramp, gaining speed in a linear fashion. Starting at the top with no speed, and linearly increasing your speed. The moment that you hit the bottom part here, the velocity would actually start decreasing in a linear fashion. Probably not quite at the same rate that it was increasing on this side. And this would be what they asked us to mark TL. I guess where it leaves, the time where it leaves the ramp. Then friction, then the net force goes from being in the direction of motion, which it was on the ramp, which causes an increase in speed. And then the moment it leaves the ramp, the net force becomes in the direction behind, in the backwards direction, because of friction, which switches the slope of this, which is acceleration, from a positive acceleration, the slope of this is acceleration, to a negative acceleration, which is slowing down until it would finally stop. All righto. That's that question. A lot of work, but it gives you a good sense of what they're looking for on these kinds of questions. All right, erase that. Now, back. Sorry. Click that. All right, this one now. An object of mass 10 kilograms is released from rest above the surface of a planet. Force of gravity exerted on the object is most nearly. So this is a speed versus time graph, right? So for a speed versus time graph, the rate of change of speed with reference to time is acceleration, right? So the acceleration is the slope of this graph. The reason I need to know that is because they've asked for the force due to gravity. The force due to gravity is called the weight. And the weight of any object is calculated by doing m times g. They gave me m. They told me it's a 10 kilogram mass, but I don't know g. As soon as I know g, I can finish my problem off by doing m times g. But if they said that this graph represents how the speed changes while in free fall because you've dropped it, then the slope of this, the acceleration, is actually the acceleration due to gravity because it's falling. So we just have to do a slope calculation. Let's pick the whole triangle because I can see that this goes right through the corner there, which is very easy to read. So I know that it's 6 seconds of motion, and then I know it gained 20 meters per second of speed in that amount of time. Change in velocity would be 20, because it started off with no speed, and delta t would be 6. 6, 12, 18, it's 3, with 2 remaining out of 6. That's 3 1/3, which would be 3.33 3, right? Because that would be 3.26, 3 1/3, 3.33 meters per second squared. Now we can just plug in the mass. Again, they told us the mass right here was 10, and acceleration due to gravity based on this graph is 3.33. That gives me 33.3 newtons as the weight of this object, or the force of gravity due to the planet's gravity, or the force due to the planet's gravity. Oh wait, 33.3, which is most near to that would be C, 35. Moving on. All right, next one. A vehicle lands on Mars, explores its surface. The average gravitational field on the surface of Mars is 3.7 newtons. So that's one thing I'm going to mention right now, is the units there. So usually when we write F equals ma, right, we can write F net equals ma. From a unit standpoint, we know F is in newtons, and we know mass is in kilograms. So that means if we solve for A's units, which we know would be dividing mass to both sides, we know A is, again, a force divided by a mass. Technically, the units would be newtons per kilogram. So that's one way of expressing the units of acceleration, which I haven't really told you. But since acceleration due to gravity on Earth is 10, the number 10, we would say that on Earth, we could say it's 10 newtons of force per 1 kilogram of mass. So that means if you have a mass of 1 kilogram, how much force would be acting on it from Earth's gravity? 10. If you have a mass that's 2 kilograms, how much force would be acting on it? Well, 10 newtons per 1, so 20 newtons. That would be the weight. 30 newtons for a 3 kilogram object, 40 newtons for 4 kilograms. So that's one way of expressing an acceleration in newtons per kilogram. It's not very frequent. Usually we reference it as meters per second squared because it represents a change in speed in meters per second per 1 second, right? Meters per second per second. But I'm just pointing out that is another unit. They made a mistake here because that should have a slash. They wrote it like this. It should say per slash. They're missing a slash there. So don't worry about the units. Just know it's referencing G. It's saying and gravitational field is just the strength of a force field, is essentially just something that can pull on something without touching it. Since Earth can pull on us when we're in the air in the downward direction without actually touching our body, that's the concept of a field, that it's able to extend its force out to something it's not in contact with, like magnets. They have magnetic fields. They can pull on each other without touching each other. Concept of a force field. So the gravitational field in strength on Earth, we know, is 10, give or take. They're saying on Mars it's 3.7 meters per second squared, but they've expressed it in terms of newtons per kilogram. The weight of the vehicle is defined as the gravitational force, which we know. Mars force pulling it down, that pulls down on it, is called the object's weight on Mars, which again would be different than what it weighs here because Earth has different gravity. Earth's gravity is stronger, so that vehicle would weigh more on Earth and weigh less on Mars. With all those things, it says select 2 answers that are true. D is definitely correct because it says the vehicle weighs less on Mars than it does here. Yeah, because there's less gravity on Mars, right? And we know that the weight of a vehicle of anything is mg, or we write the force of gravity is mg. So if g is less, which it is, as they said in the problem, then the weight must be less. The other one that I haven't really talked about a lot this year would be this one. The idea that when you go closer and closer to a planet, if this is a planet and there's some spaceship approaching a planet, the Earth's gravity pulls on this. The force of Earth's gravity pulls on it directly towards the Earth. And as that rocket gets closer and closer, the amount of pulling force actually increases. Becomes a much stronger force the closer they get, because Earth's gravity acts like magnets do, which is when they're closer together, there's a more pulling force. When magnets are further apart, there's less pulling force. So when two objects like the planet and the rocket get closer and closer, the actual weight, I know it's hard to believe and think of, but it's true. Since the pulling force gets stronger, based on this picture I'm drawing here, the weight of the spaceship actually increases. So that's why B is correct. The vehicle's weight increases while it descends, because descends means it's getting closer to Mars. Since the gravity force from Mars gets stronger as it gets closer to the ground, the weight would be increasing. So that's B and D. All right, next question. All right. Another free, this is the only other one that was a free response, but I don't mind doing this now. It says a student strikes a block at the bottom of a ramp, giving it an initial speed up the ramp, as shown. So there's got some speed coasting up the ramp. Someone just smacked it, and it has some speed now coasting up the ramp. There is friction, it says, between the ramp and the block, so it's a frictional ramp. And it slides a distance x up the ramp, and then slides back down the same distance. On the dots below, which represents the block, draw and label the forces to our free body diagram. So as it goes up the ramp, we're not showing the force from the student that hits it. We're showing after it's been hit and it's coasting up the ramp. We know that the normal force is this direction. We know that the gravity force is straight down. We know that it's coasting up the ramp. That's what this says, up the ramp. That means the friction force would be down the ramp. That would be Hmwk for the sliding friction. When it's going down the ramp, we still have a normal force. We still have weight. But now, since it's going down the ramp, the frictional force would be in the other direction. Equal in amount to the amount that it was before going up, just opposite direction. Magnitudes would be equal for the frictional force going up or down. That's it. B, the block takes time t up to slide up the ramp, and it takes a certain amount of time to come back down the ramp from the top back to the bottom. Let's compare them. Which is greater, the time for it to go from the bottom up to the top of the ramp, or the time for it to go from the top back down to the bottom of the ramp? Well, it depends on the acceleration, how rapidly it's speeding up, or how rapidly it's slowing down. We know that on the way up the ramp, it's decelerating at a certain rate. And we know that when it's going down the ramp, it's accelerating at a certain rate. Right? But we know that the acceleration, the rate of either deceleration or acceleration, is equal to the net force divided by the mass in both cases. So really what we have to think about is, in which cases there are larger net force going up the ramp, or is there more net force when it's coming down the ramp? Well, that becomes only obvious, or never obvious, but only becomes clear when you think about the components. So gravity, of course, pulls down the ramp, Fgx, right? And that means if you're going up the ramp, if V is going up the ramp, then the frictional force is this way, and so is Fgx. So that means there's two forces that are in the opposite direction of motion. The gravity force pulling down the ramp and the frictional force. However, when we look at going down the ramp, when V is going down the ramp, we can say the same thing. We could say there's gravity there and there's a gravity force pulling it down, Fgx. But notice that the friction force would actually be the other way. And those are not in the same direction. This is in the opposite direction of this. Where originally on this side, they're in the same direction. So where would those be combined to be the greatest value? Because net force is the combination. When they're both in the same direction or when they're both in opposite directions, when do two vectors provide the greatest magnitude? Right? It's like saying, I've got a 5 Newton vector plus a 2 Newton vector. When they're together in the same direction, we know we get 7 Newtons versus we have the same 5 Newton vector, but now we got the 2 Newton vector going the other way. So that gives us actually only 3 Newtons. So when does the forces provide the greatest combination when they're in the same direction, of course. Which means that in this scenario over here, going down the ramp, the rate of acceleration is greater than how quickly it slows down going up the ramp. So I'm just going to make up a number just to conceptualize that. Maybe we calculated on this going down the ramp scenario when we find that the acceleration is 5 meters per second squared. So it's going to gain 5 meters per second each second going up, let's just say. But then when we did it over here, which we're not going to bother doing, we're just solving this conceptually. Maybe when we do it over here, which is going up the ramp, so sorry, I'm realizing I made a mistake here. I drew it the wrong way. I'm sorry. This was supposed to be the other way. This one here. So going down the ramp, the forces are. Oh, I'm just kind of confused by looking at my v vector. That shows me that I shouldn't make them so close together. Sorry. This is correct. Going down is up, and then going up is. All right. I just disregard everything I said. I was looking at the wrong arrow. I didn't make a mistake. So the point is that on this side, going up the ramp that I just did, those two forces are in opposite directions. The friction force is up the ramp, while F(gx) is down the ramp. On the other hand, on this side, which we're referencing going up the ramp, we have two forces that are in the same direction. So we might find that the acceleration, which would technically be negative, but it would be a larger number. It might be like 8 meters per second squared, meaning it's losing speed at a greater rate than how much speed it gains per second when it goes up the ramp. I'm sorry, when it goes, sorry, it's down. I'm so sorry. When it goes down the ramp. And this is when it's going up the ramp. So my point is, again, when going up or down a ramp, the net force isn't the same in both cases. When going up a ramp, which is on the right side of my screen, both the friction force and F(gx) are pointing down the ramp. They combine to provide a larger unbalanced force, meaning that it'll slow down really quickly because it's going up the ramp. It'll slow down, but at a fast rate. When it's coming back down the ramp, which I've modeled on the left side of this page, those forces are not in the same direction. Coming down the ramp, Fk is up and Fgx is down. They won't combine to produce as much net force, and therefore the acceleration rate will be a little less in magnitude than the deceleration rate was. With that in mind, how will that affect the time? Right? How will that affect how long it takes to go all the way up versus all the way down? So in this case, when we have it going up the ramp on the right side of my screen, since the acceleration rate is really quite high, it's losing speed very quickly, this would be a small amount of time because it loses speed at a very rapid rate comparatively to that large loss of speed per second causes a small amount of seconds for it to finally lose all of its speed. Where on the other side, when we're coming down the ramp, it'll take more time to come down that same distance because it's not gaining speed as quickly in magnitude. So I know that's confusing. It is a little confusing, but the conclusion is that when you're going up a ramp, which is the right side of my screen here, that will be more amount of, I'm sorry, I didn't mean to write that. That will be less amount of time, less than t going down. So since it's a small amount of time, we would refer to that to being less in amount of time. Less than the amount of time it takes to come down. All right, I'm going to erase that. And then the last part, would you be having you would have to be writing that out. What your rationale was. I would say what I was saying. Going up the ramp provides two forces that are down the hill when you're sliding up a ramp. And those two forces both pointing down the hill, which is the gravity, FGX and FFK, provide a more of a combined effect for the net force. A lot more unbalanced force going up the hill. Compared to when you're going down the hill, there's less unbalanced force, because when you're going down the hill, the frictional force is actually up the ramp and the FGX is down the ramp. So the amount of unbalanced force is, in that scenario, less. And that produces two different accelerations. Loosely using the word acceleration, meaning speeding up or slowing down, which is called acceleration, because we can just talk magnitude. And since those different acceleration rates they're different if you're going up or down depending on the net force, the amount of time that it takes to either go 5 meters up a ramp will be different than the amount of time it takes to come back down the same 5-meter ramp. In your own words, you would have to try to describe that. Okay. Notice their wording. In a clear, coherent paragraph length response, which is defined by AP College Board as being 3 to 5 sentences. I would err on the side of 4 or 5 if I were you, not 3, but depends on the question. But again, for students that are writing 1 or 2 sentences, and there are some students in the last exam that did do that, you were not meeting the criteria that I was trying to suggest you should try to hit. A clear, coherent means easy to read. Clear meaning not confusing. Coherent meaning like the logical sequence of descriptions. But in a paragraph length, right? All right, moving on. In this one, we're asked for the to evaluate what the acceleration. This is the pivot lab that we did. It's the modified Atwood machine. And the question is, what would the acceleration versus net force look like, assuming that the net force was continually changed by changing the amount of weight that's hanging over here? And if you repeated it in multiple trials, changing the amount of weight each time and measuring the acceleration just like we did for the pivot lab, what graph would properly show the acceleration, how the acceleration is affected by the net force on the system? This is the acceleration of the system. They're directly proportional to each other. That was Newton's second law. It's part of Newton's second law. Acceleration of a system is directly proportional to the unbalanced amount of force acting on it, called net force. And that acceleration of the system is inversely proportional to the total mass of the system. But they're not referencing mass here. They're talking net force. So since acceleration of the system is directly proportional to the net force, this is the graph. That's what a directly proportional graph looks like. Doubling one doubles the other, tripling one triples the other. When one's 0, the other's 0. Directly proportional. Moving on. Right. In a lab, a block weighs 80 newtons. And it says there is a 32 Newton force pulling it to the right. That's measured by some scale that you're using to pull it, just a measuring tool. We know the normal force is the same as the gravity force down. They tell us that the gravity force is 80 newtons, which tells us the normal force is also 80 newtons. But we know that those cancel, right? These cancel. So when we're looking at net force, they also say that there's friction between the block and the surface is negligible. So there's or we're assuming there's no friction. The question was, what is the acceleration of this system or this block? We know it's equal to the net force acting on it divided by the mass of that thing. The net force would be 32 newtons because that's the amount of unbalanced force, since these, again, are in cancellation with each other. The only thing we have to be careful of is to not put 80 newtons, which is what they wrote in this area, in for mass, because the mass is not 80 newtons, that's force. We'd have to work out what the mass was by saying, okay, the weight, which is what they gave us, is 80. The mass would therefore be 80 divided by 10. I think it's 8, says 80. I wrote over it. It looks like an 80, which would have been 8 kilograms. right? And so that's the mass. You have to do that separately on the side, and then plug that in right here. 32 divided by 8 is 4. So the acceleration should be 4. You see. Here, this is one of the harder questions. We're asked to figure out or create an expression for the acceleration of the system, recognizing that it's moving to the right, but it has a friction force that's to the left. Something's pulling it with a rope, perhaps. I see tension there. So we need to remember that this component would be t sine theta because of this angle here. And this component pulling it rightward would be t cos theta, right? And so in general, when we say how do we get the expression for the acceleration, it's the net force divided by the mass, right? The net force, since this is accelerating sideways, moving to the right, we're interested in the net horizontal force. The net horizontal force is really Tx, pulling it to the right, minus F, right, which is to the left. So we know there's a tension force, again, pulling it leftward, but some friction force pulling it to the left. This will be minus, this will be plus. Let's call the direction of motion plus. But there's an expression for the Tx. Tx is t cos theta because it's adjacent to that angle, right? So technically I would have Tx minus F divided by m. But there's an equation or expression for Tx, it's t cos theta minus F divided by m. Now just based on that, I see t cos theta. That makes this one out because this has t sine theta in it. The b is gone. The other three have start with a cos theta, just from deductive reasoning. You can conclude that b must be wrong. What makes this far more difficult is now having to work out what the normal force is. The reason we have to work out what the normal force is because the friction force, the force of sliding friction is equal to the coefficient of friction times the normal force. And when things are just moving sideways because something's pulling it straight to the right, then this is just mu times m times g. But the force is not straight to the right. It's up at an angle. It complicates things. So the normal force is not going to be mg the way it usually would be, since there's somebody pulling it up. There's something pulling up that up a little bit to reduce some of the pressure underneath it, because the normal force is referencing to the force underneath it. This amount, remember, is t sine theta, because this is the angle that. So it means that the total upward forces, the normal force plus ty, have to be equal to mg, because all upward forces have to equal all downward forces, because it's not moving up or down, it's just moving to the right. So that means the y component forces, the net force in the y direction is 0. Of course, they're balanced vertically. So to take this and run with it, we would say, all right, the normal force, which is up, plus ty must be equal to mg, right? We're solving for the normal force. Why are we doing that? Because we need it. We need it over here. I'm just putting n, fn. But we'd end up with mg minus ty. But ty, remember, is this piece right here. T sine theta. That is the normal force. Equation for the normal force in magnitude. So that means if we want to get an equation for the sliding friction force, which we need to, the sliding friction force would be mu k times this business on the right, mg minus t sine theta. That's an expression for ffk, right? Which means when I combine all my results all into one, which is asking a lot, This is a challenging question. Don't feel bad if you struggle with it. Very challenging, in my opinion. So that's the equation for FFK, right? We knew we had an acceleration which was going to be Tx minus F, right? Divided by the mass, because that's the net force. Tx is technically T cos theta minus the friction force, which is this big piece right here, Hmwk mg minus T sine theta. This whole piece is the friction, sliding friction expression, all divided by m. That's a theta. It's a theta over there. It kind of ran off the screen. T sine theta. So I have to stare at all that stuff. Gosh, looks like D. I see T cos theta. I see minus mu, and then mg in parentheses mg minus T sine theta, all divided by m. Ew. Yeah. Yeah. If you didn't get that one, don't feel bad. Very difficult, very challenging. A lot of understanding to try to work through that. All right, moving on to the next one. I'm getting there. Getting there. The system shown above. Oh, that's the modified Atwood machine. Release from rest. Friction is negligible. Good, they don't have to worry about the friction. Acceleration of the 4 kilogram block sliding on the table. They want to know the acceleration of the 4 kilogram block, which is also the acceleration of this, because it's a system that's tied together. They all have the same acceleration, right? This should be good. You guys should be good with this. We know that there's an amount of unbalanced force over here, which is mg. We know that this guy's weight is balanced with the normal force. They're not of interest. We're not interested in the tension force because those two tension forces cancel. They're equal in amounts, but opposite direction. The only amount of unbalanced force after having done this pivot interactive lab, I hope you recognize, is the weight of the hanging object, which means that the acceleration of the system, which I always recommend doing the system approach, is equal to the net force on the system, all divided by the mass in total of the system. So the net force, the only unbalanced amount of force, is that. And the mass of the system is just the sum of those two masses. This is the acceleration of the system. Doesn't matter who they asked for. The acceleration of the guy on top of the table, the acceleration of the guy that's falling, doesn't matter. It's the same acceleration. They gave us the mass of both. So M1 is going to be, remember, just M1 is, just be careful not to reverse it. That's the hanging guy. So that would be 2 times 10, all divided by 4 plus 2. 2 plus 4, 4 plus 2, I don't know if I did it the right way, but it's the sum of their masses. So you have 20 divided by 6. 6, 12, 18. Looks like that's the same number of 3 and 2 sixths. Just 3 and 1/3 is 3.33. Choice C. All right, moving on. Almost there. Almost there. A toy doll and a toy robot are standing on a frictionless surface facing each other. The doll has a mass of 0.2 kilograms and the robot has a mass of 0.3 kilograms. The robot pushes on the doll with a force of 0.3 newtons. What is the acceleration of the robot? This is a Newton's third law combined with Newton's second law. Newton's third law is that if one thing pushes on another thing, they feel equal forces. So if this is one person pushing on, another person that's just sitting there with their arms down, that the amount of force, this is person A and this is person B, the amount of force on person B is equal but opposite in direction to the force on A. Doesn't matter if you're actively trying to push or not. Just by being a human, having a body and someone pushing on you, even if you didn't know they're going to push you, your body will automatically push back on them with equal amounts of force but opposite direction. It's an important piece of information because they say the robot pushes on the doll with 0.3 newtons of force. And then they don't say, what is the acceleration of the doll? They're like, oh, they're trying to confuse me. The robot pushed on the doll with a force of 0.3 newtons. Now they're switching it. What is the acceleration of the robot? So we need to know that the force for both of them is 0.3 newtons. This is the force they both feel. So the acceleration of the robot, I'll put R for robot, is equal to the net force on the robot divided by the mass of the robot. The net force on the robot would be 0.3 newtons because, again, the normal force and the weight force are going to cancel. For the person that's standing, those are not of interest. So the net force is just 0.3 divided by, what are we talking about? The robot. The robot had a mass of 0.3 also. Okay, 0.3 divided by 0.3, that's 1. So that would be the acceleration rate during the push. As soon as their hands separate, or the bodies and hands are no longer in contact, obviously the acceleration would continue. So the person's, both of their bodies would accelerate in opposite directions at that, I shouldn't say both at that same rate, which is worth pointing out, but both of their bodies would accelerate away from each other for only the time that they're in contact, of course. Which one would have the greatest acceleration? Not both the same. They both feel the same force, but they both wouldn't feel the same acceleration. Remembering that acceleration is inversely proportional to mass, right? That's Newton's other part of Newton's second law. So which object had the more mass would actually have less acceleration. So it looks like the robot was heavier. The robot had more mass. So that means the robot's acceleration was 1, right? If we did calculated this acceleration for the, whatever it was called, the doll, it would have been the same net force of 0.3, but the doll's mass was actually only 0.2, which is 1.5. So the lighter doll would have a greater acceleration than the heavier robot. Not part of the question, but I think worth knowing. They could ask that. Which one during the push accelerates with the greatest rate? The lightest one, the one with the least mass, that has the least inertia. Moving on. Astronaut is in deep space relative to a nearby space station. The astronaut returns to the space station. The student makes the following claim. The astronaut should position her feet pointing away from the space station. Then she should repeatedly move her feet in the opposite direction, like swimming almost with your feet, but there's nothing out there. Just floating, swimming and floating. The claim is that this action will propel the astronaut toward the space station. Is this correct? No, it's certainly not correct because you need to push on something that's external to you in order for that external thing to push on you. Like you push on a wall, the wall pushes on you. There has to be something external to your body that you interact with in order for your body to move, at least move linearly towards the space station. You can certainly wave your arms around and stuff while you're floating, do whatever you want with kicking, but it ain't going to cause your center of mass to move at all. Center of mass is the center of your body, so stay right in that spot while you wave and kick like crazy. If it's in water, of course, as you pull the water and throw the water backwards, which we do with our arms while we swim, the water then propels you forward because you're pushing on water, you're interacting with something that's outside of you, and that water pushes you forward because you're pushing the water backwards. In outer space, there's nothing to interact with. That would never work. C, the astronaut's feet are not exerting a force on another object, so there's no external force. D, the astronaut would move away. No, certainly not. C, no, the astronaut's feet are not exerting a force on another object. Yeah, so there's no external force. Yeah, to accelerate the astronaut towards space. C. Good old Atwood machine. Of course, what is the acceleration? That's what they love to ask. Remember, it's the system again. So we just need to know that the amount of force pulling here is, I'm going to call this one M1. We'll call this one M2. So this amount of force is M1G. This amount of force is a little less, which is M2G. I know it's a little less because it's 2 kilograms compared to the 1 kilogram. So I know there's going to be some difference in those two pulling forces because you always focus on both ends of the system when it's a system of things connected by a rope, right? So we know which way is it going to go? 3 kilograms is more than 2 kilograms, so this thing is going to go down, and this guy is going to go up. So let's call the downward direction plus, right? Which means that this other guy's downward direction would have to be minus, because his direction of plus eventually becomes that way. Plus has to curl around and become plus down like that. But just know there's a difference, right? There's a difference in their weights, and that's the unbalanced amount of force, right? So the acceleration of the system is equal to the net force on the system divided by the mass of the system. The net force would be, since they're moving downward, I'm going to call that, moving in that direction, call that plus. It'll be m1g, that means this one is plus, minus m2g, all divided by m1 plus m2. Technically, you could factor out your g and say it's m1 minus m2, all divided by m1 plus m2. So a very well-known formula that you may want to at least be familiar with. Sorry, that's kind of messy in the corner there. But if we're calculating it, it's just a percentage of g. They said any system that's moving just due to gravity can only move with an acceleration that's less than g, which is why when you're looking at the numerator, m1 minus m2, and then the denominator is m1 plus m2, the denominator will always be bigger than the numerator, right? The addition of two numbers will always be bigger than the subtraction of those two numbers, which means this thing as a whole is always a number less than 1, like 5 divided by 8, right? Let's say the two numbers were, I don't know, 4 and 2. Adding them together gives me 6. Subtracting them gives me 2. 2 6 is a number that's less than 1, 0.33, right? So that whole thing here is just a percentage feature. It just provides you with a percentage of g. So we'd have to find out their masses. It was 3 and 2, right? 3 minus 2 divided by 3 plus 2. 1 divided by 5. 1 divided by 5 is not on here. Did I make a mistake? What did I do? 3 minus 2 divided by, oh, I'm sorry, times g. Yeah. Sorry. So it's 1/5 of g, right? G is 10. Sorry, running out of space there, but g is 1. So it's 1/5, which would be 2a. Another error I noticed. They're asking for the acceleration. Oh no, so sorry. Take that back. Yeah, I didn't even fully read the question. My apologies. The blocks are initially at rest and then released at 0 seconds. What will the speed of them be 2 seconds later? So my apology. If we know the acceleration is 2, which is true, I had to still do all this. What would the speed of the system be 2 seconds later? Well, 1 second later, they'd have a speed of 2 meters per second. 2 seconds later, they'd have a speed of 4 meters per second. So the answer is B, right? B equals a delta t, right? The acceleration came out as 2, as we said, and it was 2 seconds of motion, then their speed would be 4 meters per second. B. All right. You guys at least had 3 days or so to do this. This is wiping me out doing this all at once, but you got to do it. You got to get it done. All right. Doing the next problem. What's happening here? Tennis ball is thrown against a vertical concrete wall that is fixed to the ground. So here's some wall, ground, and a ball is thrown against a wall. How does the force exerted by the ball on the wall compare to the force exerted by the wall on the ball? Remember, Newton's third law says regardless of how big or heavy these two objects are, if they interact with each other, the force will be equal, but they both feel equal amounts of force, but in opposite directions. So they didn't talk about opposite directions, they were just referring to magnitude. So it's equal amounts of force, even in this, craziest cases, like a truck, a Mack truck that's moving along at 50 miles per hour collides with a mosquito that's flying along in the middle of the street, and the mosquito splats up against the windshield. Which object, the mosquito or the truck, felt the greater amount of force? Of course, everybody would naturally want to say the bug because it got killed and it's tiny. Nope. The bug felt the same exact amount of force as the truck. The reason that the bug got so destroyed due to that force is because it has such a small mass, and the force divided by mass, which is a very small mass, became a huge acceleration, enough to kill the bug. The reason the Mack truck didn't change its speed very much, which is acceleration, is because its mass is so huge. A tiny amount of force generated from sliding up a bug against your windshield divided by a huge mass would be an extremely small acceleration. For a very small duration of time, it would essentially have no effect on the speed of the truck. Remember that in magnitude, the two objects will always have the same amount of force on them, but opposite direction, regardless of how big or small they are. That's all for that trick question. A ball is moved from Earth to a planet that has gravitational acceleration that is double that of Earth. There's twice as much gravity on some planet out there. How does the gravity force on the ball when it's on this new planet compare to the gravity force on the ball when it's on Earth? The gravity force, known as the weight of an object in magnitude, is equal to m times g. Which means that it's the weight, or gravity force, is proportional to g. So if you go somewhere where there's twice as much gravity, there's twice as much gravity force, twice as much weight. So that would be a gravitational force on the ball when it's on this new planet will be double the amount of force that the ball felt when it was on Earth. A block is pulled along a surface with negligible friction by a spring scale that exerts a force F on the block. A spring scale, again, is just has a little hook on it. Show it to you in class if anybody asks. And when you pull, the spring kind of moves and is able to show you how much force is being pulled on the hook. People use it as fishermen use it to hang fish to determine what the weight of their fish is, like taking the hook and going over the gills or the mouth with it. Or the gills. All right, so anyways, a spring scale is hooked onto something, pulling it to the right, negligible friction. The mass of the block is 4 kg. The spring scale reads 10 newtons. Which of the following free body diagrams properly represents the forces it feels while it's pulled sideways along this table that has minimal friction? Well, we know the normal force and the gravity force have to be equal since it's being pulled to the right. And let's see, they all represent that idea. They do. All of these, oh, sorry. So that's why I had the extra piece, which was here. They all have equal up and down forces. So that doesn't help us at all, which they should. They all have to be equal up and down forces. Oops, what happened? I think the thing that we have to reference is the spring scale is pulling with 10 newtons of force. What is the weight of this block? It says that the force pulling it to the right, sorry, I don't know why I'm using that thick one. The force pulling it to the right is 10 newtons. What does it weigh? The weight is mg, which is, they said it's a 4 kilogram block, which is 40 newtons, which means that to correctly reference these two forces, it would actually have to be a small amount of force this way and 4 times as much force going down, right? Because 10 newtons is only 1/4 40 newtons. So we need to find image that shows that the up and down forces are 4 times longer than the rightward spring force. Well, not the first one. Those are all 1 box long. The second one, remember, we're trying to find one that has a downward vector that's 4 times longer. Ooh, C. 4 units down, 4 units up, 1 unit to the right. That matches. that meets the ratio that we're looking for. So C. C would be the correct answer for that problem. All right. Race. Only a couple more, I think. Oh, I do that every. All right. Diagram below above shows somebody lifting some object. They start by holding it out, and it's not moving. And the normal force is the force from the hand pushing. Oh no, sorry. Yeah, no, that's right. The hand pushes up on the box with a force called the normal force. They say that the box therefore must push on the hand because it's Newton's third law. If the hand pushes the box up, the box must push the hand down. And they're calling that force FH, for the force that the hand feels from the box. FG represents the weight of the box. The child then begins to raise the box with an increasing speed. After it's just held out like this in the stationary, of course, if it's stationary, these two forces would be equal to cancel out. But as soon as they start lifting up to increase the speed as they lift, what statement would correctly model the forces if that's the case, if they're lifting it with an increasing speed? Well, for one, if it's being lifted with an increasing speed, we know there must be more upward force than the downward force, right? There has to be extra upward force than downward force so that the net unbalanced amount of force would be that amount. We imagine Fg being subtracted away from Fn, right? And then it would accelerate up. So we know there's going to be more upward force than weight, but they're asking about what about Fh, the force that the person's hand feels. The hand feels a force in the downward direction because the box feels a force in the upward direction, and they're interacting with each other. So the force that the hand feels will always be equal to Fn. Fn is on box. Fh is on hand. Right? Those are the two things that are interacting, the box and the hand. They'll both feel equal amounts of force, but opposite in direction. However, when they accelerate upward, when he starts to accelerate it upward, this upward normal force will increase so that there's, right? Originally, if they're balanced, it's just sitting there. As soon as this increases, there's now an upward net force, and it will accelerate upward. So our answer has to incorporate the idea that the force that the hand feels would be equal to Fn, which A and B both state Fh equals Fn. No other ones incorporate that idea. And the secondary idea is that Fn is larger as the box is being raised because of this idea. Fn is larger when it's raised so that there's an unbalanced force between Fn and Fg so that it actually accelerates and gains speed because that's what they said. They said it begins to raise the box with increasing speed. So the correct answer would be A. All right. Oh, boy. All right, and then the last, hopefully the last one. Almost on the last one, two more. All right, there's 3 blocks being pushed by a force P, as shown in this image. Fc is the magnitude of the contact force between the blocks 2 and 3. Ff is a frictional force, Fn is any normal forces, and Fg are the weights. Which of the following free body diagram is correct for block 3? Well, we know block 3 has a weight, which is Fg. We know there's a normal force in this equal amount up, that's Fn. We know block 2 is pushing it to the right, right? If this whole thing is being pushed. Block 3 does not feel object P, whatever force is coming from P, it just feels block 2 pushing on it, right? So block 2 is pushing block 2 like that, pushing block 3 to the right. This is the force from block 2. And they did say there's some friction, so we know that there's going to be some friction to the right. I'm sorry, friction to the left if it's moving to the right. You just have to recognize that they called the force from block 2 Fc. That's all. So we just need an FC, a less friction force to the left since there's more force to the right since it's moving to the right, an FN and an FG. No P. No. Block 1 is the only one that feels P. That force gets communicated through block 1 pushing on block 2 and block 2 pushes on block 3. But again, the force from block 3 feels to the right is only the force from block 2, which is pushing on it. So anything that includes P should be ignored. It's not a possible answer. So A is out. B is out. This is one of those ones that I had cut it off. So I have to go to 18, which is up here. C is ding, 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 ding. It's C. All right, because D is almost right, but there's no friction force being represented there. So it would have to be C. Okie dokie. One more question. I believe. I'm finally through this. All right. What's going on here? Oh, yeah. So now we're on to 19, the last question. 3 objects can move along a straight level path. The graph below shows the position D of each object plotted versus time. The sum of the forces on the object is 0. Remember that the sum of the forces, they're called the net force. This is called the sum of forces. But more specifically, it's really the vector sum of the forces. To add these forces up into the vectors. And also that's sometimes written sum of the forces. Whichever way you would like to write it is equal to M times A in a certain direction. If we're talking about horizontal, this is straight level path, and X means straight and level, horizontal motion. Which of these represent no net force? Right? And so in this case, we know there's acceleration, which means there is, because it's curved, right? There is a net force. This one is not even moving because the distance distance is not changing from some position. Well, that means the acceleration is 0 for that object. It could be just your cup sitting on a table. That's not supposed to be that long, so sorry. Cup sitting on a table like this. It's balanced. The acceleration is 0, and the net force is 0. The distance away from the wall, let's say, would look like this. That one has to be included because they said which scenario or graph represents something that has 0 sum of forces being 0. As well as if something is moving like a ice hockey puck, moving along like this at a constant speed, and there's no friction. And this is the normal force, and this is the gravity force. There's no friction, there's no forward force, it's just momentum and inertia is carrying it to the right. This would also be no net force. What would a distance versus time graph look like for this? It would be linear, gaining equal distance per second. So both of these would have to be included, 1 and 2. We have finally arrived at the end of that fairly long review, but necessary. I hope you've taken the time to watch as much as you possibly could of this. Best case scenario, all of it, but if not, parts that you needed to see. And I hope you find it helpful, and we will continue in the next class with an opportunity for you to ask any additional questions you might have. All right, have a good day. Time for me to eat some lunch.